Imagine standing atop a hill overlooking ancient Rome, watching as millions of gallons of fresh, clean water flow effortlessly into the city every single day. Water that traveled dozens of miles across valleys and mountains without a single pump or engine. That's not just a marvel of ancient engineering, that's one of humanity's most breathtaking achievements. A system so advanced that it still leaves modern engineers scratching their heads in awe. The Roman aqueducts weren't just structures of stone and mortar. They were lifelines, symbols of power, and masterpieces of precision that shaped an empire and changed the course of civilization forever. What's truly astonishing is that these aqueducts were built over 2,000 years ago, long before the invention of modern tools, computers, or even basic machinery. Yet, they delivered water with a level of accuracy and reliability that would challenge even today's engineers. How did the Romans accomplish something so monumental with such limited technology? How did they move water across vast distances, maintaining just the right slope for gravity to do all the work, without any of the advanced instruments we rely on today? These questions aren't just about history, they're about human ingenuity, ambition, and the relentless drive to conquer nature itself. In this video, we're going to journey back in time to uncover the secrets behind these incredible structures. We'll explore how the Romans designed, built, and maintained their aqueducts, revealing the brilliant minds and clever techniques that made it all possible. From the mathematics behind their gentle slopes to the hidden tunnels and arches that defy the landscape, you'll discover why these aqueducts were far more than just water channels. They were a testament to what humans can achieve when curiosity, determination, and innovation come together. So settle in, because we're about to unravel one of history's greatest mysteries, and by the end, you'll see the ancient world in a whole new light. But to truly grasp the scale of their ambition, we have to step into the shoes of a Roman citizen around 300 BCE. At that time, Rome was not yet the gleaming marble metropolis of legend. It was a crowded, bustling, and rapidly expanding city built across 7 famous hills. Its lifeblood was the Tiber River, weaving through the city center. For centuries, this river provided water for drinking, cooking, and cleaning. But as Rome's population exploded from a few 100,000 to well over 1 million people, the Tiber faced a crisis. It became the city's main sewer, a receptacle for waste from homes, workshops, and even the bustling livestock markets. The water grew increasingly polluted and unsafe, a breeding ground for disease that threatened the very heart of the empire. This water crisis coincided with a cultural revolution in Roman society. The Romans didn't just see water as a basic necessity for survival. They viewed it as a fundamental pillar of civilization itself. Their daily life was built around public water consumption. Grand, elaborate bath complexes were more than just places to get clean. They were social hubs, community centers, and symbols of status where Romans from all walks of life would gather to discuss politics, conduct business, and relax. These immense structures, with their hot and cold pools, libraries, and gardens, required a staggering volume of water to operate. Furthermore, the Roman ideal of urban life demanded that clean, fresh water be freely available to all citizens through countless public fountains that adorned nearly every street corner. This wasn't a luxury, it was a public right and a demonstration of imperial power and generosity. The city's growth and its citizens' soaring expectations created an impossible equation. The local springs and wells were utterly insufficient, and the polluted Tiber could never meet the demand for clean water. Rome was literally dying of thirst, in the midst of its own grandeur. This dire situation presented the Roman engineers and leaders with an immense challenge, but also a breathtaking opportunity. They refused to be limited by their geography. Instead of trying to conserve the meager local supply, they made a radical decision. If there wasn't enough water in Rome, they would go out and find it elsewhere, and they would bring it to the city, no matter the distance or the obstacles in their way. This ambitious vision, born from necessity and fueled by imperial pride, set the stage for one of the most audacious engineering projects the world had ever seen. So, with that grand vision in place, the immense challenge became a matter of practical execution. The first and most critical step was answering a deceptively simple question. Where do you find enough clean water for 1,000,000 people? The Romans couldn't just tap into any river or lake. The water had to be pristine, abundant, and, most importantly, located at a higher elevation than the city itself. Every single drop of water that flowed into Rome did so powered solely by gravity. This meant the search for the perfect water source was an expedition into the unknown, a task that required a unique blend of intuition, observation, and rudimentary science. Roman engineers, known as aquarii, became masters of hydrology long before the term even existed. They weren't just builders, they were detectives of the natural world. Their primary target was never rivers, which were prone to seasonal flooding, silt, and contamination. Instead, they sought out the origin points of rivers, natural springs bubbling up from deep within aquifers in the surrounding mountain ranges. They believed spring water, filtered through layers of rock and earth, was the purest and healthiest, what they called aqua dulcis, sweet water. Finding these hidden springs required a profound understanding of the landscape. The aquarii would spend weeks, sometimes months, surveying the countryside. They looked for telltale signs of water, lush, green vegetation in an otherwise dry area, specific types of trees like willows or reeds that thrived in damp soil, and even morning mists hovering over particular valleys. They observed the behavior of animals, knowing that herds would gravitate toward water sources. Some historical accounts even suggest they hired water dowsers, though the engineers likely relied more on their empirical observations than any mystical means. But finding water was only half the battle. The true test was proving its quality and quantity. The engineers conducted simple but effective tests. They would dig observation pits near a potential spring to watch how quickly water filled them, gauging the flow rate and the spring's reliability during different seasons. To check for purity, they would leave a sample of the water in a bronze or lead vessel overnight and observe if it left any residue or developed a bad taste. They even had a clever method for comparing the clarity of different water sources by pouring them onto a clean piece of white wool fabric and seeing which one left the least amount of sediment or stain. The most brilliant aspect of their search, however, was their long-term thinking. They didn't just look for a spring that flowed strongly in the summer. They needed one that would remain consistent during dry seasons and years of drought. This often meant venturing deep into the mountains, far from Rome itself. The Aqua Marcia, one of the most famous aqueducts, drew its water from springs over 91 kilometers away. By going to these great distances, they weren't just solving an immediate problem. They were future-proofing the city's water supply for centuries, securing sources that were not only pure but also resilient, ensuring that the lifeblood of the empire would never run dry. Once the perfect source was confirmed, the real test of Roman engineering genius began, plotting the course. Convincing water to flow dozens of miles downhill is simple in theory, but achieving it across the rugged, unpredictable Italian landscape was a monumental task of precision and patience. The goal was a gradient or slope, so slight it seems almost imperceptible to us today. For the aqueduct to work, the channel needed to drop between 1 and 3 feet for every mile of distance. To put that in perspective, if you were to walk an entire mile alongside the aqueduct channel, the drop in height from start to finish would be less than the length of your average ruler. This minuscule slope was the golden rule. Any steeper and the water would flow too violently, eroding the channel walls and arriving in a turbulent, wasteful surge. Any shallower and the water would simply stall, becoming a stagnant pond in the conduit. Achieving this perfect, gentle descent across 50 or even 60 miles of wilderness required surveying on a scale that is difficult to comprehend. The lead surveyor, the librator, was the unsung hero of the entire operation. His most vital tool was the corbels, a marvel of simple, elegant precision. Imagine a wooden bench about 20 feet long, supported by 2 pairs of legs with plumb bobs hanging from each corner. A water channel ran along the top of the bench. The librarian would set the corbels on the ground and carefully pour water into its top channel. By observing the water level in this channel and adjusting the legs with wooden wedges until the plumb bobs hung perfectly even, he could confirm the device was level to an astonishing degree of accuracy. Historians and engineers who have reconstructed it found it can achieve a level plane with an error margin of less than 1 part in 1,000, a feat rivaling many modern tools. But the corbels was just the beginning. The surveyors also used a simpler, more portable instrument called a groma. This was a cross-shaped tool with plumb lines hanging from each arm, used for sighting straight lines and marking right angles across the countryside. With these tools, the surveying team would begin their painstaking work. They'd start from the water source, which was always their highest known point, and begin plotting a path towards Rome. A team of assistants would mark the line with poles and flags, moving forward in increments. The librator would constantly check his corbels, calculating the necessary drop over the next segment. He wasn't just looking at the ground in front of him. He was visualizing an imaginary line, the rigor aquae or water line, that had to maintain its constant descent through forests, over hills, and across deep valleys. This is where their skill truly shone. The landscape was never a smooth downhill slide to Rome. It was full of obstacles. When they encountered a small hill, they had a choice: divert the channel around it, adding precious, undesirable length to the route, or tunnel directly through it. For a large valley, the options were to take a long, looping detour following the contour of the land, or to commit to building a massive bridge-like arcade to carry the water channels straight across the gap. Every decision was a complex calculation of labor, materials, time, and that all-important gradient. A detour might be easier to build, but it risked making the overall route too long, potentially losing the vital elevation needed to reach the city. A tunnel through a hill was back-breaking work, but it preserved the direct line and the elevation. A valley arcade was a breathtakingly expensive project of stone and concrete, but it was often the only way to maintain the straight, efficient course that gravity demanded. The surveyors had to see the future, mapping not just the land as it was, but the immense structure they would impose upon it, all while holding an unwavering imaginary line in their mind that fell no more than a few inches every 1,000 feet. This focus on the precise gradient leads to one of the most common misconceptions about Roman aqueducts. Our imagination, fueled by photographs and films, instantly conjures images of those iconic, towering stone arcades marching across the European countryside. While these above-ground bridges are the most visually striking remnants of the system, they represent only a small fraction of the total construction. The vast majority of the aqueduct's journey, often up to 90% of its length, was completely invisible, hidden safely beneath the earth. The Romans were incredibly pragmatic builders, and tunneling the conduit underground was their default, preferred method for a host of brilliant reasons. First and foremost was preservation. By burying the water channel, they sealed it away from the relentless Mediterranean sun, preventing enormous losses from evaporation. This was a critical consideration for a system carrying a precious resource dozens of miles. Just as importantly, the earth acted as a natural insulator, keeping the water cool and refreshing. This was no small benefit in a culture that prized cold, fresh drinking water and needed to keep the public fountains and baths supplied with pleasantly cool water, even during the hottest summer months. Beyond climate control, the underground tunnels offered unparalleled protection. A channel running in the open air, even if just a shallow ditch, was vulnerable to becoming contaminated by dust, debris, agricultural runoff, and animals. By enclosing the water in a buried pipe, the engineers safeguarded its purity from source to city. This subterranean design also provided formidable security. An exposed aqueduct was a glaring strategic weakness. An enemy army or even local saboteurs could easily breach the channel and cut off the water supply, potentially besieging a city without ever laying siege to its walls. A tunnel hidden underground, often with its access points concealed, was virtually immune to such attacks, making the city's lifeline incredibly resilient. The construction of these underground sections, known as specus, was a massive undertaking in itself. For most of the route, crews would dig a deep trench. At the bottom, they would carefully construct the channel itself. The preferred method was to build a U-shaped trough from stone or Roman concrete, which was famously waterproof. This trough was then covered with flat stone slabs or a vaulted stone ceiling, creating a completely enclosed tube. Finally, the entire structure was buried under backfill, leaving no trace on the surface except for periodic access shafts. These shafts, called puttae, were vital for construction and, later, for maintenance crews to enter the tunnel and clear any blockages or repairs without having to excavate the entire length. When the surveyor's unwavering line met a substantial hill or mountain, the Romans didn't waver. They simply tunneled straight through it. These quarrying operations were some of the most dangerous and labor-intensive aspects of the entire project. Teams of workers would attack the rock face with iron picks, wedges, and hammers, often working by the dim light of oil lamps in suffocating, dusty conditions. The rock and debris were hauled out through the puttae shafts, which served as vital ventilation and escape routes during construction. The accuracy achieved in these tunnels is astounding. Crews digging from opposite sides of a mountain would meet in the middle with a misalignment of only a few inches, a testament to the surveying skills of the librator and his team who guided them from the surface. This extensive network of underground channels was the true backbone of the system, a hidden, protected highway that delivered its cargo safely and efficiently across the vast Italian landscape. Yet for all their brilliance working underground, the Romans couldn't just tunnel through every obstacle. When their unwavering survey line met a deep, wide valley, there was no alternative but to rise above it. And it's here that we encounter the most iconic image of Roman engineering, the soaring stone arcades. These monumental bridges were not the default choice, but the final, spectacular solution when geography left no other option. Their construction was a breathtaking display of logistical planning, material science, and a deep understanding of the forces of nature, all accomplished without modern machinery or mathematics. Before a single stone was laid, the work began far below the surface. Roman engineers understood that the immense weight of a stone aqueduct bridge demanded an unshakable foundation. For each pier that would support the arches, crews would dig down through the soft topsoil until they reached what they called solium, a firm, stable layer of bedrock or hard-packed clay. If the valley had a river running through it, this presented a formidable challenge. They would drive massive wooden piles into the riverbed and then construct a watertight cofferdam, a temporary enclosure made of closely fitted timber planks sealed with clay around the worksite. They would then use water wheels or buckets on an endless chain, powered by workers treading on them, to bail out the water from inside the dam, allowing them to excavate the riverbed down to a solid foundation, all while the river flowed around them. Upon this firm base, they would lay a foundation of thick, waterproof Roman concrete, often mixed with crushed pottery and brick to create an incredibly durable hydraulic setting mix that could resist water erosion. This concrete was poured into the excavated pit, and sometimes, for extra stability in wet ground, they would first drive a forest of sharpened oak piles into the earth to consolidate the ground before the concrete was added. This created a massive, stable block that would serve as the unyielding anchor for the pier rising above it, designed to withstand not only the static weight of the bridge, but also the dynamic forces of flooding rivers and even seismic activity. The true genius of the arcade, however, lies in the form that rose from these foundations, the arch. The Romans didn't invent the arch, but they perfected its use on a colossal scale. The arch is a masterpiece of physics because it is a pure compression structure. Each stone in the arch, known as a voussoir, is meticulously cut into a tapered wedge shape. When all the voussoirs are set in place and the final central stone, the keystone, is dropped in, the weight of the entire structure and the water above it is transformed. Instead of pushing straight down, the force is redirected outwards and downwards along the curve of the arch, channeling the immense load into the massive piers on either side. This elegant distribution of force is what allowed these slender-looking structures to support thousands of tons of masonry and water for centuries. Building the arch itself was a carefully choreographed process. A temporary wooden frame, called centering, was first constructed to hold the voussoirs in place until the keystone was inserted. Skilled masons would then carefully set each stone, ensuring every joint was perfectly tight. The mortar used was minimal. The strength came from the precise fit of the stones and the brilliant compression mechanics of the arch itself. Once the keystone was in place and the mortar had set, the wooden centering could be removed, and the arch would stand entirely on its own, a self-supporting testament to Roman precision. These arches were almost always built in a repeating series. This was not just for aesthetic grandeur, it was a critical structural choice. A single, massive arch spanning a wide valley would have generated tremendous outward thrust at its bases, requiring enormous, impractical abutments to prevent it from collapsing. By using a series of smaller, repeating arches, the outward thrust from each one counteracted and balanced the thrust from its neighbor. This created a tremendously stable, interlocking system where the forces were contained and channeled efficiently down through the piers into the waiting foundations. The rhythm of arches we see in ruins today is a direct expression of this brilliant structural logic, a visual diagram of forces in perfect equilibrium. Upon this sturdy skeleton of arches, The actual water channel was then constructed. It was built as a continuous, gently sloping masonry box, lined with waterproof cement to prevent leaks. To protect the water from the sun and contamination, this channel was almost always covered with stone slabs or topped with a vaulted roof. From a distance, the aqueduct arcade would have appeared as a solid wall, with only the occasional opening hinting at the life-giving river flowing silently across the top. The final result was not merely a utility, but a powerful symbol of Roman order imposed upon wild nature, a breathtaking marriage of raw power and graceful elegance that continues to inspire awe 2 millennia later. Now, while the grand arcades and hidden tunnels form the skeleton of this vast network, the true lifeblood of the system flowed within the channel itself, a masterpiece of material science known as the specus. This was the carefully engineered conduit that actually carried the water, and its construction was just as critical as the structures supporting it. The Romans understood that a leaky aqueduct was a failed aqueduct. Every drop lost through seepage was a wasted effort and a threat to the city's supply. Their solution was a revolutionary waterproof concrete so effective, so incredibly durable, that it has defied the centuries. We can walk up to sections of these channels today, 2 years later, and find them still holding water as if they were poured just yesterday. This miraculous material was called opus signinum, and its recipe was a testament to Roman practicality and innovation. At its heart was a simple but brilliant formula. They would take a standard lime mortar mix and combine it with an aggregate of coxiopsto, which is essentially incredibly fine particles of crushed terracotta bricks and pottery. This wasn't just using broken chunks. They would painstakingly grind the ceramic material into a powder almost as fine as sand. When this powder was mixed with lime and water, a fascinating chemical reaction occurred. The silica and alumina within the ceramic fragments would react with the lime to form stable calcium silicate and aluminate hydrates. In simpler terms, this reaction created a concrete that was not just hard, but virtually impermeable. The ceramic particles filled the microscopic pores in the mortar, creating an incredibly dense, non-porous matrix that water simply could not penetrate. It was a form of concrete that actually cured harder and more waterproof the more it was exposed to water, making it the perfect material for an aquatic environment. The final surface was so smooth and slick that it also minimized friction, allowing the water to flow with maximum efficiency on its long journey to the city. The application of this opus signinum was a meticulous process. Masons would first construct the U-shaped trough of the channel from brick or stone. Then, they would apply a thick underlayer of rough mortar to create the perfect shape and slope. Finally, they would add a final smooth finishing coat of the signature pinkish red opus signinum, often polishing it with trowels or even stones to achieve a glassy, seamless surface that offered minimal resistance to the flowing water. This attention to detail ensured there were no cracks, ridges, or rough spots where sediment could build up or where turbulent water could erode the channel over time. The effectiveness of this material cannot be overstated. It was a primary reason the aqueducts could operate for centuries with minimal maintenance. While organic growth and mineral deposits called sinter did gradually build up on the walls, requiring periodic cleaning, the structure itself remained sound and watertight. This incredible longevity wasn't an accident. It was the direct result of a deliberate and sophisticated understanding of materials, a classic example of Roman engineering where every single component, from the massive arch down to the microscopic ceramic dust in the mortar, was thoughtfully designed to serve a specific purpose and stand the test of time. Achieving that near miraculous consistency of slope across such vast distances was perhaps the single greatest challenge the Roman engineers faced. It demanded not just brute force, but an almost artistic level of precision. To understand the sheer scale of what they were accomplishing, consider this. A gradient of 1 foot per mile translates to a slope of roughly 0.02%. For a 50-mile-long aqueduct like the Aqua Claudia, this meant the entire system had to drop just 50 feet from its mountain spring source all the way to its destination in Rome. An error of just a few feet in their calculations at the source would mean the water would either arrive with destructive force or, more likely, simply fail to flow at all, stalling somewhere in the countryside. The margin for error was virtually non-existent. This is where the Roman surveyor, the librator, truly earned his reputation. His toolkit, while simple by our standards, was exquisitely effective for the task. His most trusted instrument was the corbates, a 20-foot-long wooden bench resting on 2 pairs of sturdy legs. Along the top of the bench ran a shallow channel. The librator would pour water into this channel, and his assistants would carefully adjust the legs with wooden wedges until the water rested perfectly level from one end to the other, verified by plumb bobs hanging from each corner of the device. A reconstructed corbates has been tested by modern engineers, who found it could achieve a level plane with an error margin of less than 1 part in 1,000, a level of accuracy that rivals many modern spirit levels. But the corbates was a large, cumbersome device for the initial setting of a line. For the day-to-day work of marking the course across the countryside, the surveyors relied on a more portable tool, the groma. This was a clever device consisting of a cross-shaped frame mounted on a vertical staff. From the end of each arm of the cross hung a plumb bob. By sighting along the strings of opposite plumb bobs, the surveyor could establish perfectly straight lines, and by turning the device 90 degrees, precise right angles. Teams of workers would move ahead of the librator, marking the proposed path with poles and flags. The librator would then follow with his instruments, constantly checking and rechecking the elevation, calculating the necessary drop for the next segment, and instructing his team to adjust the grade accordingly. Their process was a masterclass in patient, incremental progress. They worked in stages, establishing a series of small, manageable straight-line segments, each one perfectly leveled and graded to maintain the overall descent. They weren't just looking at the ground directly in front of them. They were constantly thinking in 3 dimensions, visualizing the rigor aqui, the unwavering water line, as it stretched invisibly through the landscape. They used a system of detailed written records and inscribed stone markers to record elevations at key points, creating a permanent log of their progress that could be referenced and verified by other teams. This meticulous, step-by-step approach allowed them to conquer seemingly impossible terrain, maintaining their critical gradient through dense forests, around hillsides, and across rolling plains, ensuring that the water would always know which way to flow. Yet for all their brilliance with gravity-fed channels and arcades, the Roman engineers faced a problem that even their most precise gradients couldn't solve: the impossibly deep valley. Imagine a gorge so vast and so profound that building a stone bridge across it would be an architectural nightmare, requiring piers of unimaginable height and a project so colossal it would bankrupt the treasury. In these extreme situations, the unwavering rigor aqui, the sacred water line, seemed to meet its end. But Roman ingenuity refused to be defeated by a mere topographical depression. Instead of surrendering to the landscape, they developed a technology so audacious, so counterintuitive, It seems to defy the very laws of physics they so meticulously followed. The inverted siphon. The principle seems almost like magic. We're all familiar with the simple siphon, perhaps using a garden hose to drain a fish tank. You suck on one end to start the flow, and water travels up and over the edge of the tank, then down into a bucket below. The inverted siphon applies this same principle, but on a staggering, monumental scale. The aqueduct channel would approach the rim of the valley and then plunge dramatically downward in a near vertical drop, carried not in an open channel, but through a sealed pipeline. This pipeline would run down the valley's side, across the floor, and then surge back up the opposite slope, where the water would miraculously emerge, often at nearly the same height it started, to continue its gentle gravity-fed journey toward Rome. The physics behind this feat is a brilliant manipulation of pressure. In a normal open channel, water is only subject to atmospheric pressure, and it can only flow downhill. But when you enclose water in a sealed pipe and send it on a downhill journey, something extraordinary happens. The weight of the water column behind it, sometimes hundreds of feet tall, creates enormous pressure at the bottom of the U-shaped dip. This pressure doesn't just push the water along. It provides the force needed to propel it back up the other side of the valley. It's a system that trades elevation for pressure, using the potential energy from the steep drop to overcome the climb on the opposite side. The real marvel, however, wasn't the concept, it was the execution. The pressure at the very bottom of these systems could be immense, enough to burst any weak pipe. The Romans needed a pipeline that could withstand forces that would shatter ordinary clay or lead pipes. Their solution was a masterpiece of material engineering called the venter or belly. They constructed the pipeline not from a single material, but from a multi-layered, reinforced pressure vessel. The most common and robust design used short, stout stone blocks, each one meticulously drilled through the center to create a perfect circular bore. These stone pipes were then joined together with lead seals or waterproof mortar, creating a continuous, incredibly strong tube. In some cases, they used multiple lead pipes bundled together for smaller systems, but for the massive municipal aqueducts, the stone venter was the technology of choice. The most famous example of this daring technology was the siphon that carried the aqua marcia across the valley of the river Anio. The pressure pipeline here plunged down one side of the valley and surged up the other, overcoming a height difference that would have been insurmountable with a bridge. The pressure at the bottom of this system was so great that the engineers had to build massive reinforced stone structures, called casella premensoria, or pressure castles, to contain and stabilize the pipes at the lowest point, preventing them from bursting under the strain. This was engineering at its most bold and sophisticated. While there were losses, a phenomenon called head loss, due to friction against the pipe walls, meant the water wouldn't quite return to its original height. The Romans calculated for this. They would start the siphon from a slightly elevated point to ensure the water had enough energy to complete its journey. The inverted siphon stands as a stunning exception to the rule of Roman aqueducts, a moment where they abandoned gentle gravity for a controlled, explosive burst of pressurized power, proving their understanding of hydraulics was far more advanced than we often give them credit for. After its long and carefully engineered journey across the Italian countryside, the water finally arrived at the city walls. But delivering this vast quantity of water to the heart of Rome was only half the battle. The true final test of Roman ingenuity was how to distribute it fairly, efficiently, and reliably to over 1 million people. This is where the system transitions from a marvel of civil engineering to a masterpiece of urban planning and social management. all orchestrated by a network of unassuming but critically important buildings called casella, or distribution castles. These casella were the command and control centers of the entire urban water network. Imagine a small, sturdy, windowless stone building, perhaps 20 feet square, strategically placed at a high point within the city, often near a major gate or at a key intersection. From the outside, it was purely functional, but inside, it housed the brilliant and final piece of the hydraulic puzzle. The main aqueduct channel would terminate here, pouring its precious contents into a large basin. This was the moment of truth, where the single, unified flow from the mountains was divided up to serve the entire city. The design of this basin was deceptively simple, but it incorporated a stroke of pure genius, a series of calibrated outlet pipes set at different heights on the wall. This vertical arrangement was the key to the entire Roman priority system for water distribution. The highest outlet pipe in the Casella Basin led to the most essential public service, the public fountains. These fountains, or lacus, were located on nearly every street corner and were the primary source of water for the vast majority of Romans who lived in crowded apartment blocks with no private supply. This design guaranteed that no matter what, the fountains would receive water first, even if the aqueduct's flow diminished slightly due to a seasonal drought or a partial blockage. The water level in the casella would drop. The lower outlets, which served less critical users, would simply run dry, while the highest outlet to the public fountains would continue to flow until the very last moment. This was a fail-safe mechanism built right into the hardware, ensuring the populace always had access to drinking water. The next outlet down, slightly lower on the wall, would feed the next priority, the immense public bath complexes. These were not mere luxuries, but fundamental pillars of Roman civic life, hygiene, and culture. While a temporary interruption to the baths would be a major inconvenience and a blow to public morale, it was not a life-threatening crisis. The water for the baths could be sacrificed to preserve the drinking supply. Below that, outlets of progressively smaller diameters served the final two categories: industrial users and private residences. Workshops for fullers, tanners, and potters, which required large volumes of water for manufacturing, were granted access, but it was a lower priority. Finally, at the very bottom, the smallest pipes led to the private homes of the wealthy elite, who had paid a substantial fee to the state for the privilege of a direct connection. This system of calibrated pipes was a physical manifestation of Roman values. It clearly prioritized public health and communal benefit over private luxury and commercial enterprise. The water commissioner, or curator aquarum, and his team of slaves could also manually control the flow using sluice gates and stopcocks within the casella, allowing for maintenance on specific lines or to temporarily increase supply to a particular district for a public festival or to fight a fire. From this central hub, a web of lead pipes, known as fistulae, would snake out through the city streets, buried beneath the pavement. These pipes were often stamped with the name of the owner or the emperor who authorized the connection, serving as a form of accountability and a way to track unauthorized taps. The entire distribution network, from the massive casella to the smallest fistula, was designed to maintain pressure and prevent stagnation. The pipes were sized to keep the water moving, and the continuous draw from public fountains ensured a constant circulation throughout the system. This elaborate, multi-tier distribution was the final, brilliant act of the aqueduct's journey. It transformed a singular torrent of water from the mountains into a finely tuned utility, meticulously managed to uphold the health, economy, and social order of the ancient world's greatest city. Of course, ensuring the water arrived in a pristine state was a point of immense pride and practical necessity for the Romans. After traveling dozens of miles through open channels and pipes, the water, while protected, could still pick up silt, leaves, or other fine debris. Delivering murky or contaminated water to the public fountains would have defeated the entire purpose of their monumental effort. Their solution to this final challenge was a sophisticated and multi-layered system of ancient water treatment, proving their engineering genius extended beyond mere transport into the realm of public health. The first and most crucial line of defense was a structure known as a piscina limaria settling tank or sedimentation basin. These were large, purpose-built reservoirs constructed at strategic points along the aqueducts route, almost always just before the water entered the city's distribution network. The principle was elegantly simple yet incredibly effective. As the fast-moving water from the main channel flowed into the expansive, calm basin, its velocity would drop dramatically. This sudden loss of speed caused the heavier suspended particles, sand, silt, and organic matter, to sink gently to the bottom of the tank. The design of these tanks was far from a simple hole in the ground. It was carefully engineered to maximize cleaning efficiency. Inlet and outlet pipes were placed at opposite ends, and often at different heights to encourage a smooth, laminar flow across the entire surface of the basin, preventing turbulence that could stir up the settled sludge. The bottom of the piscina was typically lined with the same waterproof opus signinum concrete, making it easy for maintenance crews to periodically enter and remove the accumulated sediment, ensuring the tank's continued effectiveness. This process of decantation, allowing water to literally clean itself through gravity, provided a massive improvement in clarity and taste before the water ever reached a citizen's cup. For an even finer level of filtration, some aqueducts incorporated a second stage, mesh filters. Historical evidence and archaeological findings suggest the use of grids or screens made of bronze or woven reeds placed at the inlets to the piscinae or at the entrance to the distribution casella. These would catch larger floating debris like leaves, twigs, or even small animals that might have found their way in the channel, acting as a coarse pre-filter before the sedimentation process. There are also accounts, particularly from the engineer Frontinus, of systems that used a series of tanks, where water would flow from one settling basin into another, undergoing multiple stages of purification for the most esteemed water sources that supplied the imperial household. This attention to water quality wasn't just about aesthetics. It was a matter of health and status. The best water, like that from the Aqua Marcia, was renowned for being cold, clear, and exceptionally sweet-tasting, a direct result of its pristine mountain source and this careful post-journey treatment. The Romans may not have understood germ theory, but they had a deep empirical understanding that clear, cool, good-tasting water was associated with health and vitality. By implementing these treatment systems, they were proactively safeguarding the well-being of the city's population, ensuring that the empire's lifeblood was not only abundant but also pure. It stands as a powerful testament to their holistic approach, where the project wasn't considered complete once the water arrived at the city gates, but only once it was delivered to the people in its most usable and beneficial form. Building and maintaining these aqueducts was only half the battle. Keeping them flowing cleanly for centuries required an equally sophisticated system of upkeep, a hidden world of maintenance that operated continuously behind the scenes. This was the domain of the aquarii, the specialized corps of water workers who served as the plumbers, engineers, and emergency responders for the entire network. Their work was vital, demanding a unique combination of physical bravery, technical skill, and institutional knowledge passed down through generations. Without these unsung heroes and the brilliant access systems designed for them, the entire magnificent enterprise would have crumbled into disrepair in a matter of years. The most critical innovation for maintenance was the network of access shafts, known as putae, which translates literally to wells. These were not wells for drawing water, but rather manholes, spaced at remarkably consistent intervals of approximately 240 Roman feet along the entire underground length of the aqueduct. This precise spacing wasn't arbitrary. It was a calculated decision to ensure that no section of the tunnel was too far from a point of entry. The putae were vertical shafts, lined with stone or brick, that descended from the ground surface all the way down to the level of the buried water channel. At the bottom, a small opening connected the shaft to the tunnel itself, creating a doorway into the dark, confined world of the Specus. These shafts served multiple indispensable purposes. First and foremost, they provided ventilation during the original construction, allowing fresh air to reach the teams of workers digging and lining the tunnels far underground. But their permanent function was for inspection and cleaning. Maintenance crews would descend into these shafts using ladders or ropes, bringing with them tools, lamps, and baskets for removing debris. Once inside the tunnel, they could patrol long sections, checking the opus signinum lining for cracks, clearing obstructions, and ensuring the vital gradient remained unobstructed. The greatest enemy of the aqueduct's flow was not major structural failure, but the gradual, insidious accumulation of sinter, a hard, crusty deposit of calcium carbonate that precipitated out of the mineral-rich spring water. Over time, this sinter could build up on the walls and floor of the channel, much like plaque in an artery, slowly narrowing the passage and reducing the volume of water that could flow through. If left unchecked, it could eventually choke the conduit entirely. The aquarii's primary task was to constantly battle this deposit, chipping it away with iron picks, chisels, and hammers. It was back-breaking, tedious work performed in cramped, dark, and damp conditions, but it was absolutely essential to the health of the system. Beyond the putae, the engineers incorporated another clever feature for major repairs: special cleaning doors or fonts. These were larger, more substantial openings built at key points, particularly where the aqueduct emerged from a tunnel or where major branches connected. Unlike the simple putae shafts, these were designed to allow for the removal of larger blocks of sinter or even the replacement of sections of the channel lining. In the event of a serious collapse or blockage that couldn't be handled from a putius, crews could use these fonts as a primary access point to bring in materials and manpower for a significant repair operation. The work of the aquarii was organized and overseen by the state, under the authority of the curator aquarum. They were divided into specialized teams. Some crews were dedicated to patrolling the above-ground arcades, inspecting the piers and arches for structural issues or weathering. Others were assigned to specific underground sections, becoming intimately familiar with every inch of their territory. There were even emergency response teams on call to deal with sudden breaches, often caused by severe weather or ground settlement, which required immediate action to prevent a catastrophic loss of water and to avoid erosion that could undermine the foundations of the entire structure. This comprehensive, proactive maintenance regime was what gave the Roman aqueducts their legendary longevity. It wasn't magic or indestructible materials that kept the water flowing for hundreds of years. It was the relentless, disciplined effort of countless anonymous workers. They operated out of sight, deep beneath the fields and streets, ensuring that the engineering marvel visible to all on the surface could continue to perform its miracle day after day, year after year, generation after generation. Their story is a powerful reminder that even the grandest visions of empire ultimately rest on the foundation of meticulous, everyday care. But who paid for these monumental testaments to Roman ambition, and perhaps more importantly, why? The construction of an aqueduct was not merely a public utility project. It was one of the single largest financial undertakings in the ancient world, a breathtaking investment that reveals the core priorities and power structures of Roman society. To understand the economics is to understand that these structures were as much political statements and tools of social control as they were feats of engineering. The primary patron for these colossal projects was almost always the emperor himself, or in the earlier days of the Republic, a victorious general or immensely wealthy statesman. Funding an aqueduct was the ultimate act of civic benefaction, known as euergetism. For an emperor, it was a direct investment in his own legitimacy and popularity. A new aqueduct bearing his name, like the Aqua Claudia or the Aqua Alexandriana, was a permanent, undeniable monument to his power and generosity, providing a tangible benefit that every citizen, from the poorest laborer to the richest senator, could experience every single day. It was a powerful piece of propaganda, a constant reminder that the emperor was the true benefactor and father of the people, ensuring their health, comfort, and pleasure. We can try to grasp the scale of this investment by translating the cost into modern terms. Though any calculation is inherently speculative, the historian Pliny the Elder records that the Aqua Marcia, built in the 2nd century BCE, cost the state treasury 7,800 sesterces. To put that into perspective, a common legionary soldier earned about 900 sesterces a year. The aqueduct's cost was equivalent to the annual salary of over 8,600 soldiers. In more relatable terms, a modest house in Pompeii could be purchased for around 200 sesterces. The Aqua Marcia cost the same as 3,900 such homes. A modern, rough estimate would place the cost of a major aqueduct in the hundreds of millions, if not billions, of today's dollars, representing a fiscal commitment comparable to a modern nation undertaking a massive space program or a nationwide high-speed rail network. This staggering sum wasn't just for materials. The largest expense by far was labor. A project spanning decades would require a small army of workers. We're talking about thousands of skilled and unskilled men, surveyors to plot the course, architects to design the arcades, quarrymen to cut the stone, masons to lay the bricks and concrete, blacksmiths to forge and maintain tools, and countless laborers to dig the trenches and haul the materials. Much of this unskilled labor was provided by slaves, a readily available resource fed by Rome's endless wars of conquest. But a significant portion was also paid, free Roman citizens who formed a specialized workforce, their employment on such a grand project providing a vital stimulus to the local economy for years on end. The funding often came from a mix of sources. While the imperial treasury frequently covered the bulk of the cost, it was also common for wealthy citizens, eager to gain social prestige and political favor, to donate large sums for specific sections or ornamental features like the grand public fountains at the terminus. Sometimes, the spoils of war were directly funneled into construction. The Annio Vetus aqueduct was famously paid for with the booty seized from the Pyrrhic victory over King Pyrrhus of Epirus, turning bloodshed into a life-giving civic resource. This economic model highlights a fundamental difference between ancient and modern public works. Today, we expect such infrastructure to be funded by the state for the public good as a matter of course. In Rome, it was framed as a magnificent gift from a powerful individual to the people. The aqueduct was a physical embodiment of the patron's virtue, their dignitas and octoritas made manifest in stone and water. The ongoing maintenance, managed by a state-appointed curator aquarum and his team, was also funded from public coffers, but the initial glory and the eternal naming rights always belonged to the benefactor. This system ensured a constant cycle of monumental construction, as each new leader sought to outdo his predecessors and leave his own indelible mark on the city, forever quenching its thirst in his name. The birth of this grand tradition of water engineering can be traced back to a single, groundbreaking project, one that emerged not from a time of peace and prosperity, but from the crucible of war. In the year 312 BC, Rome was locked in a desperate struggle against the Samnites, a conflict that was straining the city's resources to their absolute limit. It was in this atmosphere of crisis that two visionaries, the censor Appius Claudius Caecus and his colleague Gaius Plautius, made a decision that would change the course of urban history forever. Instead of pouring all of the state's treasury and manpower solely into the war effort, they would embark on a daring domestic project of unprecedented scale, the construction of Rome's first aqueduct, the Aqua Pia. The very concept was revolutionary. No city on the Italian peninsula had ever attempted to import water from such a distance. Previous settlements relied on local springs, wells, or rivers. The Aqua Pia shattered this paradigm, establishing a new principle that would define Roman civilization for a millennium. If the resources aren't where the people are, you build a path to bring them there. Appius Claudius, a man known for his political shrewdness and iron will, saw this project not just as a utility, but as a powerful political statement. It would demonstrate Rome's resilience, its innovative spirit, and its commitment to its citizens, even in the midst of external threats. This dual-purpose thinking serving both practical need and political ambition would become the blueprint for all future imperial construction. Choosing the route for this first attempt was a monumental exercise in risk management and clever engineering. The source they selected was a collection of springs located just over 16 kilometers away, near the modern town of Colonna. While this distance seems modest compared to the 90-kilometer behemoths that would follow, for its time it was a staggering undertaking. The engineers faced a critical topographical challenge. The shortest, most direct path to the city ran through the notorious Pontine Marshes, a vast malaria-ridden swamp that was both geologically unstable and dangerous for work crews. A more obvious route might have followed higher, healthier ground, but this would have added many extra miles and, more importantly, precious elevation loss. The Roman solution was a masterstroke of practical engineering. They chose the direct route through the marshes, but they designed the aqueduct to run almost entirely underground. For approximately 90% of its length, the Aqua Pia was a hidden tunnel, dug deep beneath the treacherous landscape. This decision brilliantly solved multiple problems at once. It protected the water supply from contamination and evaporation, shielded the construction crews from the swamp's unhealthy vapors by working in shielded trenches, and perhaps most cleverly, it hid the entire vulnerable system from Rome's enemies. An open channel would have been an easy target for the Samnites' T.O. Chinese letter, but a buried pipe was nearly invulnerable. This established the enduring Roman preference for subterranean construction, proving that the most brilliant engineering is often the engineering you never see. The final stretch of the aqueduct's journey presented its own unique hurdle. The Aqua Appia entered Rome at its highest point, the Capitoline Hill, but its destination was the bustling Forum Boarium, the cattle market, and the Portus Tibernus, the city's main river port, both located at a much lower elevation. To navigate this drop without losing control of the water's flow or violating the gentle gradient, the engineers constructed a massive supporting structure called the Arcus Appiae. This wasn't the graceful arcade of later years. It was a formidable, functional elevated channel that carried the water down the slope of the Aventine Hill, delivering it precisely where it was needed most. The impact of this first aqueduct on daily life in Rome was nothing short of transformative. The Aqua Appia delivered an estimated 75,000 cubic meters of water every single day, a volume that must have seemed miraculous to a population accustomed to the polluted Tiber and scarce local wells. This water was not distributed to private homes. Its purpose was overwhelmingly public and commercial. It supplied the bustling heart of the city's economy, the ports and the markets, ensuring that commerce, the lifeblood of a growing power, would not be hampered by a lack of clean water. It also supplied water to the low-lying districts that had previously suffered the most from the Tiber's contamination, providing a cleaner, more reliable source for the people who lived and worked there. The success of the Aqua Appia did more than just quench a city's thirst. It ignited an imperial tradition. It proved that such a project was not only possible but immensely beneficial, both for the public good and for the prestige of its builders. Appius Claudius himself secured a place in history, with his name forever attached to this life-giving marvel and to another monumental project he commissioned in the same sensorial term, the Via Appia, the famed Appian Way. Together, the road and the aqueduct represented the two defining pillars of Roman power: the ability to move armies and goods swiftly across land, and the ability to move water effortlessly across country. This first successful project created a template of ambition and engineering courage, setting off a wave of aqueduct construction that would, over the next 5 centuries, see 10 more major aqueducts built, each one longer, higher, and more daring than the last, until Rome truly became the Caput Aquarum, the capital of the waters of the world. Rising from the pristine limestone springs in the Anio Valley, the Aqua Marcia wasn't just another aqueduct. It was a statement of imperial excellence. Commissioned by the Praetor Quintus Marcius Rex, its completion in the year 140 BCE marked a new era of ambition. While earlier aqueducts like the Appia and the Anio Vetus were functional triumphs, the Marcia was designed from the outset to deliver something Rome had never had in such abundance: truly superior water. The source was chosen with fastidious care, selecting springs bubbling up through volcanic rock at an elevation so high that its water would possess a legendary chill and a clarity praised by poets and engineers for centuries to come. This was aqua dulcis, sweet water, at its finest, and bringing it to the city required an engineering masterpiece. Its journey began over 91 kilometers, or 56 miles, from Rome's gates, a distance that posed an unprecedented challenge for its surveyors. To maintain the vital gradient, the channel had to drop only about 160 feet over its entire length, a slope of just 1 foot per mile. Guiding this gentle descent across such a vast and rugged landscape required near superhuman precision. The route was a masterclass in strategic pathfinding, weaving through the Sabine Hills, navigating around natural obstacles, and plunging through solid rock in miles of tunnels, all to preserve every precious inch of elevation. The water's path was a testament to the librator's skill. an invisible line of perfect decline etched across the Italian countryside. The most breathtaking solution along this route was employed to cross the deep valley of the river Anio. Here, the engineers faced a choice: a long, meandering detour that would sacrifice hard-won elevation or a direct, terrifyingly bold approach. They chose the latter, constructing one of the most magnificent arcades the ancient world would ever see. This wasn't merely a functional bridge. It was a monument in its own right. Soaring arches of massive tuff and travertine blocks carried the water channel hundreds of feet above the valley floor, a breathtaking sight of raw power and graceful geometry. The scale was staggering, a man-made mountain range built to serve a single, flowing purpose. Sections of this colossal arcade still stand today, their enduring strength a silent tribute to the Roman mastery of arch and pier. Upon finally reaching the city, the Aqua Marcia's terminus was a celebration of its own quality. It emptied into a grand casella on the Viminal Hill, and from there, its famously cold, clear water was prioritized for the most esteemed public uses. It supplied the fountains in the city's wealthiest districts and was a primary source for the lavish imperial bath complexes, where its refreshing temperature was a coveted luxury. The aqueduct's reputation was so exalted that the Emperor Augustus later supplemented its flow by tapping additional springs. And even the notorious Emperor Nero, known for his excess, built a special branch just to supply water to his private villa. The Aqua Marcia set a new standard, proving that an aqueduct could be more than a utility. It could be a source of civic pride and a symbol of the refined quality of life that defined the peak of the Roman Empire. If the Aqua Marcia set a new standard for quality, then the Aqua Claudia and its sister aqueduct, the Anio Novus, represent the absolute zenith of Roman imperial ambition, a breathtaking declaration that no physical or financial constraint could limit the empire's vision. Initiated by the Emperor Caligula in 38 AD and completed by his successor Claudius 14 years later, these two projects were conceived not just to meet the city's needs, but to utterly overwhelm them, delivering a volume of water so colossal it dwarfed all previous systems combined. They were the crowning achievements of a mature empire, built not with the practical frugality of the early republic, but with the boundless confidence and resources of absolute power, pushing Roman engineering to its absolute limits. What made these two aqueducts so revolutionary was their radical approach to sourcing water. The Aqua Claudia, true to the established preference for purity, drew from two deep, cold springs in the Anio Valley, its water celebrated for its excellence. The Anio Novus, however, broke the mold entirely. Its name, meaning New Anio, reveals its audacious source. It tapped directly into the river Anio itself, the very river that flowed past Rome and had been deemed too polluted for use centuries earlier. This seems like a catastrophic regression, a bewildering choice for a civilization that had pioneered the search for pristine springs. The sheer audacity of this decision reveals a critical evolution in Roman engineering philosophy and capability. They were no longer just seeking the best water. They were solving the problem of volume by any means necessary, confident that their system could now handle the challenge of purification on an unprecedented scale. To make the turbid, seasonal waters of the Anio River potable, the engineers implemented the most sophisticated and massive sedimentation system the ancient world had ever seen. Just after its intake, the Anio Novus was diverted into two enormous, parallel settling tanks called piscini limeri. These were not simple basins. They were massive, reinforced concrete reservoirs designed to slow the river's flow to a near standstill. Here, the heaviest silt, sand, and debris would settle out over a journey that took days, not hours. The water was then released from the top of these tanks, drawing off only the clearest water while leaving the sediment behind to be periodically dredged by maintenance crews. This system was so effective that the purified water of the Anio Novus was then deemed clean enough to be mingled with the superior springs of the Claudia for the long journey to Rome. This hybrid approach, combining a vast, less pure source with immense settling infrastructure, showcased a new level of systematic thinking, managing water quality at an industrial scale. The journey of these twin aqueducts to Rome is a story written in stone and concrete across the Italian landscape. For much of their 68-kilometer route, their channels ran side by side, one stacked above the other in a single monumental utility corridor. This itself was a logistical marvel, a testament to the centralized planning and sheer manpower the empire could now command. Their path was a relentless, straight line towards the city, overcoming every obstacle with breathtaking boldness. When they encountered the soft, unstable plain near Rome, the engineers didn't divert, they built. They constructed a mammoth subterranean conduit of concrete and rubble work, a buried fortress strong enough to resist the shifting ground and maintain its perfect gradient. Their most iconic achievement, however, was conquering the final approach to the city. To cross the low-lying plain between the Alban Hills and Rome's eastern gate, they erected the Porta Maggiore. This was not merely an aqueduct bridge. It was a triumphant double-decker arcade of such staggering proportion and strength that it also served as a fortified city gate. The lower tier carried the Aqua Claudia, while the upper tier carried the Anio Novus, thundering over the heads of everyone entering or leaving the city. Built from massive, rough-hewn blocks of travertine stone, the Porta Maggiore lacks the refined elegance of later marble monuments. Its power is raw, muscular, and undeniable, a brutalist statement of imperial power that shouted to all who passed beneath it that Rome commanded the very elements. This structure alone, still standing majestically today, encapsulates the entire project, unstoppable force channeled with impeccable precision. The statistics behind these aqueducts are almost incomprehensible. Together, the Aqua Claudia and Anio Novus delivered an estimated 290,000 cubic meters of water to Rome every single day. To visualize that, imagine a continuous stream of water wide enough and deep enough to fill an Olympic-sized swimming pool every 3 to 4 minutes, 24 hours a day, 365 days a year. This deluge increased Rome's total water supply by nearly 50% overnight. This wasn't just about meeting demand, it was about creating new possibilities. This immense volume of water was primarily directed to the Transiborum region, the district across the Tiber River, which had previously been underserved. It fueled a massive expansion of the city's iconic bath complexes, including the baths of Caracalla, and supplied countless new public fountains, enabling Rome to grow in both population and grandeur. The Claudia and Novus were the engines that powered the city's golden age, proving that with enough water, even the greatest metropolis on Earth could continue to reach for the sky. Yet the most stunning testament to this engineering philosophy exists not in Italy, but in the rugged landscape of southern France. While Rome itself was the heart of the empire, its principles and prowess were exported to every corner of the known world, and nowhere is this more visibly spectacular than at the Pont du Gard. This colossal three-tiered bridge, soaring over the Garden River Valley, was not a standalone monument but a single, vital link in a 50-kilometer aqueduct that supplied the thriving Roman colony of Nemesis, modern-day Nims. It represents the absolute peak of the aqueduct builder's art, a structure of such perfect proportions and breathtaking audacity that it continues to dominate the landscape 2 millennia after its construction, serving as a powerful symbol of Rome's ability to reshape nature itself to serve human need. Constructed in the middle of the 1st century AD, the aqueduct to Nimes was a monumental undertaking for a provincial city, a clear statement of its importance and wealth within the empire. The challenge was immense: to bring fresh water from the abundant springs of Uzes, located to the north, all the way to the city's growing population. The most direct route, however, was barred by the deep and wide gorge of the Garden River. A long detour to find an easier crossing would have added many extra miles to the journey, sacrificing precious elevation and making the entire project potentially unworkable. The Roman engineers, in their characteristic fashion, rejected the notion of compromise. Their solution was to build straight across the chasm with a bridge of such staggering scale and elegance that it would become one of the most iconic structures of the ancient world. The statistics of the Pont du Gard are enough to inspire awe even today. It stands 49 meters tall, roughly the height of a 16-story building, and stretches 275 meters across the river valley. Its construction required an estimated 50,000 tons of limestone, each block quarried from a nearby site and meticulously cut by hand before being hoisted into place with a complex system of wooden cranes and pulleys, all without a single ounce of mortar. The entire project is a masterclass in precision stonework. The massive blocks were so perfectly cut and fitted that they remain held in place by gravity and friction alone, a testament to the incredible skill of the local Celtic masons who built it under Roman direction. The genius of the design lies in its 3 distinct tiers, each serving a specific structural and functional purpose. The lowest tier is a formidable bridge in its own right, consisting of 6 immense arches that serve as the foundation for everything above. This base was designed to withstand the Garden River's notorious seasonal flash floods, which could transform a gentle stream into a raging torrent in a matter of hours. The piers of this level are strategically aligned with the natural flow of the river, their upstream edges sharpened into cutwaters to slice through the force of the current and prevent debris from building up against them. This level was so robust and wide that for centuries it served as a toll bridge for foot and cart traffic, a secondary function that continued long after the aqueduct above had fallen into disuse. Rising from this mighty foundation is the 2nd tier, with 11 slightly smaller but still monumental arches that echo the rhythm of the first. This middle section acts as a crucial transition, gracefully narrowing the structure as it ascends and providing a stable platform for the final, most important level. It is here that the visual mastery of Roman proportion becomes apparent. The architects understood that a sheer, monotonous wall of stone would have appeared clumsy and oppressive. Instead, they created a dynamic facade by varying the arch widths and the arrangement of the pillars, introducing a subtle rhythm and lightness that makes the massive structure seem to soar rather than simply loom. The crowning achievement is the 3rd and uppermost tier, a row of 35 smaller arches that finally carried the water channel itself. This top section is the reason for the entire colossal endeavor, and its construction demanded the utmost precision. To maintain the vital, gentle gradient of the aqueduct, this top deck had to be perfectly level from one side of the valley to the other, a surveying marvel achieved across such a vast gap. The water channel itself, the specus, was enclosed within a protective housing and lined with the characteristic pink, waterproof opus signinum mortar to prevent leaks. The entire structure narrows dramatically at this top level, dramatically reducing its wind resistance and overall weight without sacrificing an ounce of strength. A decision that showcases a sophisticated understanding of load dynamics and material efficiency. What makes the Pont du Gard truly transcendent, however, is not just its scale but its astonishing aesthetic harmony. This is not a brutish, utilitarian pile of rocks. It is a work of art. The architects employed subtle optical refinements to correct for visual distortion. The lines that appear straight are actually slightly curved. The spans between the arches are not perfectly uniform, and the piers are not completely vertical. These intentional imperfections were calculated to make the structure look perfectly straight and balanced to the human eye from a distance, a technique that would be rediscovered by Renaissance architects over 1,000 years later. The result is a bridge that feels both impossibly powerful and incredibly graceful, a perfect marriage of raw force and elegant form that has captivated everyone from Roman generals to modern-day tourists. It stands not as a ruin, but as a lasting monument to the idea that even the most practical infrastructure could be, and should be, beautiful. While the Pont du Gard exemplifies the harmonious fusion of form and function, another aqueduct, located far from Rome's core, stands as a perhaps even more stunning monument to raw, uncompromising engineering pragmatism. Journey to the ancient city of Segovia in Spain, and you will witness a structure that seems to defy not just time, but the very logic of construction itself. The Segovia Aqueduct is breathtaking in its simplicity and staggering in its endurance. A masterpiece built without a single drop of mortar, its colossal granite blocks holding fast through sheer precision and brilliant design for nearly 2 years. This aqueduct is a powerful testament to the Roman talent for local adaptation. Unlike the projects in and around Rome, which had access to the revolutionary opus signinum concrete and vast imperial resources, the builders in the provincial territory of Hispania had to work with what was available. Their genius lay in recognizing the incredible strength of the local granite and the skill of the local craftsmen. Instead of attempting to replicate the concrete-lined channels of Italy, they conceived a structure that would derive all its strength from the perfect cutting and meticulous placement of stone. The result is a soaring arcade of 166 arches, stretching over 800 meters long and reaching a height of 28 meters at its tallest point, all held together by gravity and friction alone. It is a titanic game of balanced blocks, a puzzle of such immense scale and perfect fit that it has withstood earthquakes, wars, and centuries of weathering without ever losing its structural integrity. The visual impact of the aqueduct is immediate and awe-inspiring. It strides directly into the heart of the modern city, its double-tiered arches creating a dramatic gateway. The lower arches are broad and muscular, providing a rock-solid foundation, while the upper tier is more elegant, a repeating rhythm of perfect curves that carry the water channel at the very top. The absence of mortar gives the entire structure a stark, powerful honesty. There is no decoration to hide behind, no filler to mask imperfections. Every joint, every block, is a visible declaration of the builder's confidence. You can stand beneath it and see the precise lines where the stones meet, knowing that for almost 2 millennia, nothing but their own perfect shape and immense weight has kept them in place. The water channel itself, the Specus, runs along the top, a testament to the same careful planning seen in all Roman projects. While the bridge is mortarless, the channel within was lined with a local, waterproof cement to prevent leaks, showing a pragmatic blend of grandiose local construction and essential Roman hydraulic principles. For centuries, this system functioned flawlessly, bringing water from the distant Frio River over 17 kilometers away to supply the city. Astonishingly, the Segovia Aqueduct remained in continuous use for its original purpose until deep in the 20th century, a fact that is almost incomprehensible when you consider its age. This wasn't a relic. It was a working piece of municipal infrastructure, delivering water to the people of Segovia for generation after generation after generation. The survival of this mortarless marvel is due to two key Roman engineering principles executed to perfection. The first is the enduring power of the arch. As with all their aqueduct bridges, the downward force of the structure is transformed into an outward thrust along the curve of each arch. In Segovia, this thrust is channeled directly into the massive, sturdy piers. The second and more specific reason is the use of a clever locking mechanism between the granite blocks. While no mortar was used, the Romans did not simply stack the stones. The tops of the lower blocks often had small, carefully chiseled protrusions, and the bottoms of the upper blocks had corresponding indentations. This system, akin to a giant stone Lego set, prevented the slabs from sliding laterally against each other, locking the entire structure into a single, cohesive, and immovable mass. The Segovia Aqueduct, therefore, is more than just a beautiful relic. It is the ultimate expression of Roman engineering philosophy applied to local conditions. It demonstrates that their genius was not a rigid set of rules, but a flexible toolkit of principles: the arch, the gradient, the prioritization of public water supply, that could be adapted using available materials and local expertise to achieve the same magnificent result. It stands not in the shadow of the Italian aqueducts, but as their equal, a roaring declaration of imperial power and ingenuity carved into the very skyline of Spain. While the Western Roman Empire faltered, the engineering spirit that built its aqueducts did not fade. It found a new, magnificent home in the East. As Rome itself declined, the new capital of Constantinople rose to become the largest and most fortified city in Europe, a megalopolis that would demand an even more sophisticated and resilient water supply. The system built to quench its thirst represents the final, magnificent evolution of Roman aqueduct technology, a network of such staggering scale and complexity that it dwarfed even the achievements of the old capital. This was not merely an imitation of past glories. It was an adaptation and improvement upon them, designed to meet the challenges of a new era and secure the survival of an empire for another 1,000 years. The challenge facing Emperor Constantine and his successors was immense. The new capital was a natural fortress, surrounded on three sides by water, but its local water sources were pitifully inadequate for a population that would swell to over 500,000. The small streams and springs on the Thracian peninsula could never support such a metropolis. The solution, true to Roman form, was to look far beyond the city walls. Over the course of the 4th and 5th centuries, a sprawling hydraulic network was constructed, tapping springs from the forested hills of Thrace, over 120 kilometers away. This was not a single channel like the Aqua Claudia, but a sprawling, interconnected web of at least 4 major aqueduct lines, featuring over 250 kilometers of channels and pipes that converged on the city from multiple directions. This redundancy was a critical innovation, ensuring that if one line was damaged or compromised, others could continue the flow, making the city's water supply incredibly resilient to both accident and attack. The crown jewel of this system, and its most visible symbol, was the Aqueduct of Valens. Completed in the late 4th century by Emperor Valens, this structure is a breathtaking example of late Roman engineering ambition. What remains today in the heart of modern Istanbul is a mere fragment of its original length, a 900-meter-long double-tiered arcade soaring over the city's traffic. In its prime, this aqueduct bridge was the final, magnificent link in a chain that stretched for kilometers, carrying water across the low-lying valleys that lay between the city's hills. Its construction is a masterclass in repurposing and pragmatism. Many of the massive stone blocks were taken from older structures in the nearby city of Chalcedon, a common practice that saved time and resources while still creating a structure of immense durability and power. But the true genius of the Constantinople system lay not in its grand bridges, but in its hidden, sophisticated distribution and storage network, which solved a problem that had plagued Rome itself: what to do during a siege. Constantinople was a city perpetually under threat, and a vulnerable aqueduct channel running for miles outside the walls was a strategic nightmare. The Eastern Roman engineers solved this with a system of massive, covered underground reservoirs, known as cisterns, built inside the city's impregnable walls. These were not simple tanks. They were subterranean palaces of water, supported by forests of columns and vaulted ceilings, capable of holding a truly staggering volume of water. The most famous, the Basilica cistern, could hold over 80,000 cubic meters of water, enough to supply the entire city for weeks. This network of cisterns transformed the city's hydrology. The aqueducts would run continuously, filling these immense reservoirs to the brim. In times of peace, they provided a buffer against seasonal droughts or maintenance issues on the long supply lines. In times of war, if the aqueducts were cut by an besieging army, the city could seal its gates and survive on its vast internal water reserves for months, effectively making it siege-proof. This brilliant combination of long-distance importation and colossal internal storage was the ultimate evolution of the Roman water system, a perfect blend of offensive engineering ambition and defensive strategic genius that helped the Eastern Roman Empire endure long after the fall of the West. To truly grasp the genius behind the aqueducts, we need to step away from the grand arches and delve into the quiet world of Roman mathematics, where a profound understanding of nature's laws was translated into precise, working formulas. This wasn't just about moving water. It was about mastering it, predicting its behavior with an accuracy that would not be surpassed for over 1,000 years. The Romans operated without a formalized theory of fluid dynamics as we know it, but through meticulous observation and brilliant empirical engineering, they developed a practical mathematical toolkit that allowed them to build systems of breathtaking efficiency and reliability. Their entire hydraulic system was governed by one non-negotiable principle: the flow of water is dictated by its cross-sectional area and its velocity. While they lacked our concept of cubic meters per second, they had their own highly effective unit of measurement, the quinaria. This was not a standard unit of length or volume, but a standardized unit of flow based on the capacity of a specific type of pipe. The quinaria was defined as the volume of water that would flow through a bronze pipe with a diameter of about 1¼ Roman digits, roughly 2.3 centimeters under a specific, consistent pressure. This ingenious standard became the fundamental module for all their water calculations, allowing engineers across the empire to speak a common language of capacity. With the quinaria as their base unit, Roman engineers could precisely calculate the necessary size of a channel or pipe to meet a city's demand. It functioned like a modern engineer's spreadsheet. First, they would calculate the total water need for a city based on its population and the number of baths, fountains, and private users. This gave them a target number in quinary. They knew from experience that a wider channel didn't just carry more water. It also increased the water's velocity due to reduced friction relative to the volume, a subtle understanding of hydraulic principles. The head engineer or librator would then use geometric formulas to determine the exact width and depth of the specus required to deliver that flow, all while maintaining the critical gradient. For a circular pipe, they understood that the cross-sectional area, and thus the flow, increased with the square of the diameter. Doubling a pipe's diameter didn't just double its capacity, it quadrupled it. This fundamental geometric insight was absolutely critical to their success. Managing water pressure was another area where their practical knowledge was exceptionally advanced, especially in their use of inverted siphons. To prevent their massive stone and lead pipelines from bursting under the immense strain at the bottom of a valley, they had to become masters of estimating force. They intuitively understood that the pressure at any point in a column of water is proportional to the height of the water above it, a principle formalized much later as Pascal's law. To calculate the wall thickness needed for a pressure pipe in a siphon, they used a rule of thumb born from experience. The strength of a lead pipe was proportional to the thickness of its walls and inversely proportional to its diameter. For a given pressure, a wider pipe needed significantly thicker, stronger walls to contain it. This is why the venter pipes at the lowest points of these systems were constructed from incredibly stout, short stone blocks with small bores, a design that could withstand pressures that would have shredded any other material available to them. Perhaps their most sophisticated calculations revolved around the interplay between gradient, velocity, and friction. They knew that a steeper slope made water flow faster, but too steep a slope would cause destructive turbulence and erode the channel lining. Through painstaking trial and error, they arrived at their golden ratio, a slope of between 1 in 200 and 1 in 5,000. With 1 in 1,000 being ideal for most aqueducts. This minuscule drop of just 1 meter per kilometer was the sweet spot that allowed water to move with enough speed to prevent stagnation and sediment buildup, but slowly enough to avoid damaging the conduit. To achieve this consistently over dozens of miles, their surveyors had to perform trigonometry in the field, using their Grommy and Corbates to measure minute angular descents, effectively calculating the tangent of the slope angle across vast distances with astonishing accuracy. This mathematical prowess extended all the way to the end user. The calibrated outlet pipes in the Casella distribution towers were a physical manifestation of their numerical control. The diameters of these pipes were not chosen at random. They were precisely calculated based on their cross-sectional area to deliver a specific flow rate in quinary to different parts of the city. A pipe for a public fountain had a larger diameter than one for a private villa, not just as a symbolic preference, but as a mathematically guaranteed priority system. This ensured that the allocated water shares, which were often sold as legal rights, were delivered with consistent fairness. The entire system, from the mountain spring to the street corner fountain, was a single, continuous, mathematically modeled machine, a testament to a civilization that could not only dream on a colossal scale, but could also calculate its way to making those dreams a functioning reality. The astonishing longevity of the aqueducts wasn't just a happy accident. It was the direct result of a materials science revolution, a series of deliberate and ingenious choices that gave Roman engineers a toolkit unlike any the world had seen before. At the heart of this revolution was their mastery of concrete, a material they didn't invent but perfected to an almost miraculous degree. While other civilizations used simple lime mortar, the Romans created a uniquely durable and, most critically, waterproof blend. Their secret ingredient was a specific type of volcanic ash, known as pulvis putiolenus, mined from the fields around the Bay of Naples near the modern town of Pozzuoli. This fine, reddish-brown powder was the key to their hydraulic empire. When this pozzolana ash was mixed with lime and water, a fascinating chemical reaction occurred that we now understand as a pozzolanic reaction. The silica and alumina compounds in the volcanic ash reacted with the lime to form stable calcium silicate hydrate and calcium aluminate hydrate gels. In practical terms, this created a concrete that was not only incredibly strong, but also hardened and gained strength over time, even when completely submerged in water. This was the complete opposite of modern Portland cement, which cures through a simple drying process and can be weakened by constant moisture. Roman concrete actually thrived in aquatic environments, making it the perfect material for lining miles of water channels. The resulting substance was so dense and non-porous that it formed a virtually impermeable barrier, preventing the precious water from seeping into the surrounding earth over its long journey. But the Romans didn't stop there. They developed a specialized, ultra-smooth version of this concrete specifically for the interior of the aqueduct channels, known as opus signinum. To create this, they would take their standard pozzolana lime mix and add an aggregate of coxiopsto finely crushed terracotta bricks and pottery. This wasn't just about using recycled materials. It was a stroke of pure brilliance. The microscopic ceramic particles filled the tiniest pores in the mortar, creating an even denser, more waterproof matrix. The final polished surface was a distinctive pinkish red color, incredibly slick to the touch, which served a dual purpose. Its impermeability prevented leaks, and its smoothness minimized friction, allowing the water to flow with maximum efficiency. This material was so effective that sections of aqueduct channel, buried for 2 millennia, can still hold water today without a single drop escaping. For the pressurized sections of inverted siphons, however, a different solution was required. The immense force at the bottom of a deep valley could crack even the strongest concrete pipe. Here, the material of choice was lead or plumbum, from which we get our word plumber. The Romans became master craftsmen in working with this malleable metal, crafting it into sheets and rolling them into pipes. The joints were a particular marvel of engineering. They didn't use screws or flanges. Instead, they employed a technique called wiped joints. A workman would carefully pour molten lead around the seam where 2 pipes met, using a cloth pad to literally wipe and mold the cooling metal into a smooth, thick, and perfectly watertight seal. These lead pipes could withstand enormous internal pressure, making them the only viable option for forcing water back up the far side of a valley. The use of lead, of course, raises the inevitable question of health risks, a topic the Romans themselves debated. The engineer Vitruvius and the statesman Seneca both noted that water carried in lead pipes seemed to cause health problems, with Vitruvius specifically recommending clay pipes for this reason. Modern analysis shows they were right to be concerned. The continuous flow of water, especially if it was soft and acidic, would have leached lead ions into the supply. However, the scale of the system likely mitigated the worst effects for the general population. The constant flow and the immense volume of water meant it didn't sit stagnant in the pipes for long periods, reducing contact time. Furthermore, the mineral-rich aqueduct water, particularly from calcareous sources, would have quickly deposited a layer of harmless calcium carbonate scale, or sinter, on the interior of the pipes, effectively plating them and creating a barrier between the water and the toxic lead. For most citizens drawing from a constantly running public fountain, the risk was probably relatively low, a calculated trade-off the Romans made for the sake of achieving previously impossible hydraulic feats. In many instances, particularly for smaller distribution lines or in areas where lead was too expensive, the Romans turned to a much safer and more humble material, fired clay. They manufactured terracotta pipes in standardized sizes, with flanged ends that could be fitted together and sealed with mortar. These were far cheaper and easier to produce than lead pipes, and were perfectly adequate for low-pressure applications. The most durable solution of all, reserved for the massive municipal inverted siphons, was the stone venter. These were short, stout blocks of stone, each one meticulously drilled through the center with a circular bore. These blocks were then carefully joined together with waterproof mortar and sometimes reinforced with lead bands, creating a continuous, immensely strong stone pipeline that was virtually indestructible and completely inert, posing no health risks whatsoever. This flexible, multi-material approach using concrete, lead, ceramic, and stone, each for the specific job, it was best suited for showcases, a sophisticated understanding of material properties that was centuries ahead of its time. Yet for all their grandeur and technical mastery, the true measure of the aqueduct's success lies not in the stone they moved, but in the daily lives they transformed. This river of imported water didn't just flow into reservoirs. It poured into the very fabric of Roman society, reshaping its rhythms, its health, and its very identity. Before this engineered abundance, water was a scarce commodity, a private struggle. The aqueducts redefined it as a public right, a shared luxury that elevated the quality of life for every citizen, from the wealthiest senator to the humblest laborer. This was a revolution in urban living, and its epicenter was the Roman bathhouse. These were not merely places to get clean. They were the ancient world's most ambitious community centers, sprawling complexes of leisure, business, and culture that were fundamentally impossible without a massive, reliable water supply. A grand imperial bath complex like the baths of Caracalla or Diocletian was a marvel of social engineering, requiring thousands of gallons of water every hour to feed its myriad pools, its hot and cold plunges, its steam rooms, and even its lavish fountains and gardens. The aqueducts made this watery paradise a daily reality. For a small, negligible fee, any Roman citizen could spend an entire afternoon in these palatial surroundings, escaping the grime and crowding of the city's dense apartment blocks. Here, in the humid air of the caldarium or the cool waters of the frigidarium, social barriers softened. Politicians networked, businessmen sealed deals, friends gossiped, and athletes trained, all surrounded by breathtaking art and architecture. The bath was the beating heart of Roman social life, a powerful democratizing force that offered a taste of imperial luxury to the common man. And it existed solely because the aqueducts willed it into being. Beyond the grandeur of the baths, the most immediate and vital impact was felt at the neighborhood level, at the countless public fountains that graced nearly every street corner. These lacus were the primary water source for the vast majority of Romans who lived in multi-story apartment buildings, or insulae, which had no private plumbing. The system's design, which prioritized these fountains above all other users, guaranteed that clean, fresh water was never more than a short walk from any home. This daily ritual of collecting water was a social event in itself, a time for neighbors to meet, exchange news, and solidify community bonds. The constant, reassuring sound of flowing water from these fountains became the soundtrack to Roman urban life, a permanent acoustic symbol of the state's care for its people. It provided not just hydration, but a profound sense of security and civic belonging, a tangible reminder that the empire's might was dedicated to their well-being. This unprecedented access to clean water also brought about a quiet revolution in public health and sanitation. While the Romans did not understand germ theory, they had a strong empirical sense that cleanliness was linked to vitality. The abundant water supply fed the city's extensive sewer system, the Cloaca Maxima, helping to flush waste away from populated areas and into the Tiber. It supplied water to public latrines, often elegant marble-lined rooms with continuously flowing water running beneath the seats, which were far more sanitary than the chamber pots and open pits common in other ancient cities. While their overall health outcomes were still challenged by other factors, this improved sanitation, combined with better personal hygiene enabled by the baths and fountains, likely reduced the incidence of waterborne diseases and epidemics that plagued other less equipped urban centers. This healthier environment, in turn, supported the city's staggering population growth, allowing Rome to sustain over 1 million people in a concentration that would have been unimaginable and unsustainable without this hydraulic lifeline. The psychological and political impact of this transformation cannot be overstated. The sight of water leaping from public fountains, the experience of bathing in immense vaulted halls, the very knowledge that this resource was freely available, it all fostered a powerful sense of Roman exceptionalism. It was a daily, physical manifestation of the emperor's power and generosity, a non-verbal argument for the benefits of imperial rule. The aqueducts were the ultimate piece of political propaganda, not written on scrolls but carved into the landscape and flowing through the city, convincing every citizen through direct experience that they were part of a civilization capable of mastering nature itself for the common good. This engineered abundance became a core pillar of the Roman social contract, proving that the empire's greatest ambition was not just to conquer the world, but to civilize it, beginning with the simple, life-giving gift of water for all. Keeping this monumental network flowing required more than just brilliant engineering. It demanded a dedicated army of specialists and a sophisticated administrative machine operating around the clock. At the heart of this effort were the aquarii, the unsung heroes of the water system. These were not simple laborers but highly skilled professionals, organized into specialized teams under the command of the curator aquarum, the state-appointed water commissioner. Each crew had its own territory and expertise. Some patrolled the soaring arcades above ground, their eyes trained to spot any hairline crack or sign of weathering in the stonework that might signal a future problem. Others were specialists in the dark, confined world of the underground specus, the water channels they knew better than the streets of their own neighborhoods. The work of these subterranean crews was difficult and often dangerous. Their primary enemy was sinter, a hard, crusty deposit of calcium carbonate that precipitated out of the mineral-rich water and built up on the channel walls over time, much like plaque in an artery. Left unchecked, this deposit could slowly choke the conduit, reducing the flow to a trickle. Armed with iron picks, chisels, and hammers, the aquarii would descend through the puttae access shafts to chip away at this stubborn crust by the dim, flickering light of oil lamps. It was back-breaking, tedious work in a damp, cramped, and claustrophobic environment, but it was absolutely essential. Other teams were on constant standby as emergency responders, ready to rush to any reported breach in the system, whether from a ground settlement, a severe storm, or even seismic activity to prevent a catastrophic loss of water and the destructive erosion that could undermine an arcade's very foundations. Overseeing this entire operation was the curator aquarum, a position of immense responsibility typically held by a distinguished senator. His role was less about getting his hands dirty and more about managing the immense logistical, legal, and financial complexities of the water supply. He was essentially the chief executive officer of Rome's water utility. His staff included not only the foremen of the aquarii, but also a small army of clerks, accountants, and lawyers. They were responsible for the system's budget, for procuring materials for repairs, and for adjudicating the countless legal disputes that inevitably arose over water access. His most critical duty, however, was upholding the sacred principle of prioritization that was physically built into the Casella distribution towers. He ensured that the public fountains always flowed first, that the baths received their allocated share, and that private users did not illegally tap into the system or take more than their paid-for allowance. This brings us to the complex bureaucracy of water rights, a system that was remarkably modern in its conception. While water from the public fountains was free to all citizens, the right to pipe a private supply into a home or business was a valuable and expensive privilege, granted by an official license from the emperor's office. These licenses were not permanent. They could be revoked for non-payment or misuse. The curator's staff maintained detailed records of every granted license, specifying the user's name, the location of the property, the legal basis for the grant, and perhaps most importantly, the pipe diameter, which directly correlated to the volume of water allotted. This was measured in the quinaria, the standard unit of flow. A wealthy senator might pay for a license for a pipe several digits wide to supply his lavish townhouse with its private bath and fountains, while a fullery or pottery workshop might secure a smaller pipe for its industrial needs. To enforce this system and prevent fraud, the Romans employed a clever form of accountability, stamped lead pipes. The lead pipes, or fistulae, that snaked from the main lines to private properties were often impressed with stamps bearing the name of the emperor under whose reign they were installed, the owner who paid for the connection, and sometimes even the lead maker himself. This was not for decoration. It was a practical anti-tampering measure. If an inspector found an unstamped pipe or a pipe with a forged stamp, it was clear evidence of an illegal tap, and the perpetrator faced severe fines. This intricate combination of physical engineering and administrative law created a resilient and fair system. It prevented the wealthy from monopolizing the supply while still allowing them to purchase convenience, and it guaranteed that the lifeblood of the city continued to flow to everyone, sustaining the health, economy, and grandeur of Rome for centuries through meticulous, everyday management. Yet even the mighty Roman Empire was not immune to the slow creep of decay, and the aqueducts, those magnificent symbols of its power and ingenuity, were among the first and most tragic casualties of its fall. The decline was not a single, catastrophic event, but a gradual unraveling over centuries, a story of fading knowledge, shifting priorities, and the brutal realities of a fractured world. The sophisticated system of maintenance that had kept the water flowing for generations began to break down as political turmoil and economic collapse drained the state's coffers and attention. The specialized corps of aquarii, the guardians of the channels, dwindled. Without their constant vigilant work, the silent enemies of the aqueducts began their final victorious assault. Mineral deposits built up unchecked, narrowing the channels to a trickle. Small cracks in the opus signinum lining went unrepaired, growing into major leaks that undermine the foundations of the structures themselves. The hidden network of tunnels, once a testament to Roman foresight, became clogged and forgotten, their access shafts swallowed by undergrowth. The final blows were often deliberate. As invading armies swept into the Italian peninsula during the 5th and 6th centuries, they recognized the aqueducts not as cultural treasures, but as strategic vulnerabilities. A city like Rome, with a population now utterly dependent on this engineered lifeline, could be brought to its knees not by breaching its mighty walls, but by severing the slender stone threads that carried its water from dozens of miles away. There are accounts of the Ostrogoth king Vitiges cutting the aqueducts during his siege of Rome in 537 A.D., a tactical move that ultimately failed to take the city but crippled its infrastructure for good. Later, during the brutal Gothic Wars, the same arches that had defied nature for centuries became military strongholds and were targeted for destruction. This systematic sabotage, combined with centuries of neglect, proved fatal. One by one, the great channels fell silent. The lifeblood of Rome ceased to flow, and the city began a long, desperate contraction, its population shrinking to a fraction of its former size as people clustered around the one reliable water source left, the polluted Tiber River. The world that emerged from the empire's shadow was a poorer, darker, and thirstier place. Medieval cities were forced to retreat to a pre-Roman reality, utterly dependent on local wells, cisterns, and contaminated rivers. The grand Roman bath culture, a cornerstone of urban social life, vanished completely, seen by some early church fathers as a symbol of pagan decadence. Public hygiene entered a steep decline, and waterborne diseases became a constant, deadly threat. The knowledge required to build and maintain such vast hydraulic networks didn't just become rare, it was utterly lost. The complex mathematics of gradient and flow, the material science behind waterproof concrete, the architectural mastery of the arch, these skills faded into obscurity, preserved only in crumbling manuscripts that few could read and even fewer understood. For nearly 1,000 years, the soaring arcades that still stood across the European landscape were not seen as inspirations for emulation, but as incomprehensible relics of a race of giants, mysterious monuments to a lost magic no one could hope to replicate. The long slumber of this knowledge finally began to end during the Renaissance, a period of reawakening that looked back to classical antiquity for inspiration. Scholars and artists, fascinated by the ruins that surrounded them, started to study these structures not as magical artifacts, but as products of human genius. The key figure in this rediscovery of Roman hydraulic engineering was the 15th century architect Leon Battista Alberti. While writing his seminal treatise, De Reedificatoria, he undertook a meticulous survey of the remains of Rome's aqueducts. He measured their gradients, studied the construction of their arches, and marveled at the durability of their concrete. Most importantly, he translated his observations into practical principles that could be applied once more. Alberti's work effectively decoded the Romans' empirical knowledge, providing a blueprint for a new generation of engineers. This revival was not merely academic. It was driven by a pressing need. Renaissance cities, growing in wealth and population, faced the same crisis that had plagued ancient Rome: rampant water shortages and rampant disease. The rediscovery of Roman hydraulic principles offered a solution. One of the first and most magnificent examples of this new-old engineering was the revival of aqueduct construction in Rome itself. Pope Nicholas V, inspired by Alberti, began a project in the 15th century to restore the Aqua Virgin, an ancient aqueduct that had been broken for centuries. This was followed by more ambitious popes, like Sixtus V, who in the late 16th century embarked on a massive campaign to restore other ancient lines and even build new ones, such as the Aqua Fellis, stitching the old imperial network back together to serve a renewed and reborn Rome. The impact of this Renaissance rediscovery spread far beyond Italy. The principles laid down by Alberti and put into practice by the papal engineers became the new standard for urban water supply across Europe. The concept of bringing clean water from distant, elevated sources via gravity-fed conduits was reborn. In France, King Louis XIV built the magnificent Maintenon Aqueduct to supply water to the fountains of the Palace of Versailles, a direct emulation of Roman grandeur. In England, the New River was constructed in the early 17th century to bring fresh water to London, explicitly inspired by Roman models. This wasn't just about copying a design. It was about relearning a philosophy that a great city requires a great water supply, and that it is the duty of civilization to harness nature through engineering for the public good. The aqueducts, once symbols of a lost empire, became the foundation for a new wave of urban development, proving that the true legacy of Roman engineering was not in the stone itself, but in the enduring power of the idea it represented. This extraordinary legacy did not vanish with the fall of Rome. Instead, it lay dormant for centuries, waiting to be rediscovered and reborn to serve a new world. The principles so brilliantly honed by the Roman engineers went on to become the absolute bedrock of modern civil engineering, forming the very foundation of how we manage and deliver one of life's most essential resources today. Our entire approach to municipal water supply is a direct continuation of the Roman model, a testament to the timelessness of their vision. The core idea that a great city cannot rely solely on its immediate surroundings, but must import clean water from distant, pristine watersheds, was a revolutionary Roman concept that every major metropolis on Earth now follows. New York City, for instance, draws its water from protected reservoirs in the Catskill Mountains over 100 miles away, a system that is, in its fundamental philosophy, a direct descendant of the Aqua Marcia. Los Angeles, with its vast and complex network of canals and pipelines stretching to the Sierra Nevada, is another modern embodiment of this ancient imperative to conquer geography in the name of survival and growth. Modern engineers continue to study these structures not as historical curiosities, but as active, living textbooks in stone and concrete. One of the most profound lessons lies in their breathtaking longevity. While some modern concrete mixtures can deteriorate in decades, especially when exposed to constant moisture, Roman concrete has demonstrated the opposite trait, growing stronger over millennia. This paradoxical durability has sparked a major field of modern scientific research. By analyzing the molecular structure of samples drilled from ancient harbor walls and aqueduct channels, chemists and materials scientists have made a remarkable discovery. The secret isn't just the pozzolana ash, it's the way the Romans mixed it. The inclusion of lime-classed small, leftover chunks of quicklime within the concrete matrix creates a fascinating self-healing property. When a tiny crack forms and water seeps in, it reacts with this leftover lime, forming new calcium silicate hydrate crystals that automatically fill the fissure. This ancient, accidental nanotechnology is now inspiring the development of self-healing concretes for modern infrastructure, from bridges to nuclear waste containment facilities, proving that 2,000-year-old knowledge could be the key to building a more durable future. Furthermore, The Roman mastery of gravity-fed systems is a masterclass in energy efficiency that is more relevant today than ever. In an age concerned with sustainability and carbon footprints, the aqueducts stand as a monumental achievement in passive engineering. They moved billions of gallons of water without a single pump, using nothing but the relentless, free pull of gravity. Modern water systems, while far more complex, still strive to emulate this principle wherever possible. The placement of storage reservoirs at high elevations to provide natural pressure for a city's water grid is a standard practice directly inherited from the Roman playbook. Engineers still speak of hydraulic grade lines and pressure gradients, which are the modern mathematical formalizations of the rigor acqui that the librator once held in his mind as he sighted across the landscape with his chorobates. Their work reminds us that the most elegant and enduring solutions are often those that work in harmony with natural forces, rather than fighting against them with brute mechanical power. Beyond the technical specifications, the aqueduct's most enduring lesson might be a philosophical one, a powerful statement about the role of public infrastructure in a healthy society. The Roman system was fundamentally built on the idea that clean, abundant water was a public right, a resource that should be managed by the state for the benefit of all citizens. The tiered priority system built in the Casella, which guaranteed that public fountains would flow even if private taps ran dry, was a physical manifestation of a social contract. This concept of public utility, that some services are so vital, they must be provided collectively and protected from private monopolization, is a cornerstone of the modern world. When we turn on a tap today and expect safe, affordable water to flow out, we are participating in a 2,000-year-old tradition that says a civilization is measured not by the luxuries of its richest citizens, but by the guaranteed well-being of all its people. The aqueducts were not merely plumbing. They were a declaration of what a society could achieve when its ambition was directed toward the common good. So why, after all this time, do these structures still capture our imagination and stand among humanity's greatest achievements? It is because they represent a perfect, rare convergence of form and function, of brute force and delicate precision, of immense ambition and meticulous care. They were not built in isolation. They were the product of a civilization that had organized itself around a set of powerful ideals: order, public health, civic beauty, and the mastery of the natural world. The aqueduct was the ultimate expression of those ideals, a machine that worked so flawlessly it became invisible, leaving only the graceful arc of a stone arch against the sky as a hint of the miracle happening above. They remind us that true engineering genius is not just about solving a problem, but about solving it in a way that endures, that elevates, and that serves generations far into the future. In the end, the water that flowed to Rome was more than just water. It was the physical manifestation of human ingenuity, a life-giving testament to what we can accomplish when we dare to think on a monumental